All right, good afternoon, everyone. Thank you for joining us for today's webinar. My name is Neil Foley, and I'm the Applications Engineer at RISE. And today I'm going to be discussing best practices for removing support material from complex parts and some things you can do during the design process to reduce the need for such supports. So I'll start with a few slides describing our technology and the benefits it provides for things like support removal. To begin with, many 3D printing technologies require a lot of pre-processing, often with expert knowledge, and our technology has a lot of built-in automations that help speed up and simplify the pre-processing phase. After printing, there is also the post-processing phase, which for many technologies can involve messy, unsafe, and costly chemicals and add several hours to your time to part. With our technology, the post-processing is very simple and safe and requires no chemicals or long processes. Simply pick off the support material by hand or with tools. Our technology also offers some excellent material properties as well as office-safe operation and marking capabilities. Our processes are safe and our cost of ownership is low, expanding the effective range of applications and markets that we can be involved in. Our technology is called augmented polymer deposition, and it offers a wide variety of applications. It involves the simultaneous extrusion of our own compound of medical engineering grade thermoplastic and jetting of special inks. First, thermoplastic is extruded as shown, forming the support structure on which the part will be built. Next, release ink is jetted between the support and the first layer of the model structure, which eases the removal of supports. Then, more thermoplastic is extruded, forming the model, and special inks are jetted between the layers of the thermoplastic to control material properties by voxel. Here's a comparison of our process of support removal versus that of a competitor's. So on the left, there's our part with supports that can often be removed just by hand. And on the right is a typical FDM part, which has soluble supports that can take hours to dissolve. So the same part that takes 25 seconds with our technology can take 3 hours with our competitor's technology. So now that I've covered the benefits of our technology for things like removing support, we're now going to look at some of the special cases where model complexity can require more advanced support removal techniques, and I'll cover how to handle these challenges and how to design parts to avoid such challenges in the future. One issue that you will probably encounter is when support is built into narrow spaces or deep cavities. It can be challenging to remove support from such areas because there is often not enough space to maneuver your tools. Another issue is broad bottom surfaces. By this, I mean that when you have a wide, raised bottom surface on your part, such as the bottom surface of the part shown here, it can be tedious to detach each piece of support because the support chunks have a high surface area on the interface compared to their low volume. You may also have had trouble with delicate supported features because removing support from those features may be forceful enough to damage them. And then there are a few other issues that may show up involving complex or inaccessible geometries, in cases such as geometries that are obstructed or internal to the part. So the first and most important issue in support removal is having the right tools. Once you have the right tools for a job, it can be very simple to solve the challenges you encounter. Shown here are the tools that I use for removing support. Most of them should have been included with your RISE 1 3D printer. One thing that I would recommend is that you sharpen the Hyde putty knife. This knife is not very sharp out of the box, and it can be less effective if you're using it to remove finished parts from the build plate or to separate models from supports. I used a basic metal file along the edge and this makes the knife much better at removing parts and flat supports. The other tools shown here are pliers, wire cutters, a scalpel, and a flathead screwdriver, and each of these serves a different purpose when you're removing support from parts. Now that we know our tools, let's get into some more specifics on using them to remove support. Shown here is the printed part that was shown modeled on the previous slide. There is a channel passing through the stem of the part, and the support in that channel can be a bit tricky to remove. A good strategy for removing support in such cases where the support is hard to access and shares a high surface area with the model is first to use the flathead screwdriver and scalpel to break the support structure up. Then remove chunks with the pliers once you've created enough space to fit them in. It can be helpful to use the scalpel to slice between the model and support in order to break out larger pieces. For broad bottom surfaces, we face a similar issue in that the support is held strongly in place with a high interface surface area and a relatively low volume to grab onto. One approach that will often work well is to focus on raising a corner using the pliers and sometimes a scalpel or screwdriver, and then hook the screwdriver or putty knife underneath and slide it across the interface, removing the support chunk. For large surfaces like this, removing several large chunks can sometimes leave behind a few stubborn pieces still stuck to the model. A scalpel can often be helpful in removing these pieces, but I have found that using the wire cutters is often better. They provide a high degree of control and much better leverage than the scalpel. You also won't have to worry about letting it slip and hurting yourself. Now, for delicate features, you will likely have to use different strategies for each case you encounter. Shown here is the same part as shown previously with small supports or with small delicate features that will require some support removal. Generally, what works well is to carefully pinch and crunch the support rather than tugging on it. This will prevent it from breaking the delicate features around it by focusing the active forces solely on the support. Once you remove the bulk of it, grasp and slowly twist the remainder off rather than pulling on it. It may also be helpful to apply a controlled counterforce with your hand to avoid flexing the feature. So that covers the major cases of complex geometries and advanced support removal techniques and how to approach them. But there is often an even better solution to the problem if you have the freedom to redesign a part. Every technology has different strengths, and if you design in alignment with the strengths of a technology, its benefits are able to shine. One of the great strengths of RISE is how easily support can be detached from our parts. But to make this benefit shine, it's best to ensure that parts are designed to maximize this benefit. Some of the strategies that help in this regard are shown here. Using self-supporting build angles and related strategies, as well as reorientation and simplification, can help to reduce or eliminate the amount of challenging support removal involved in finishing a part. This approach may increase the amount of pre-processing involved in designing a model, but it can greatly reduce the amount of post-processing required to finish each part. The first strategy is to design parts using self-supporting build angles, which eliminate the need for support. The default self-supporting build angle in RISE software is 45.5 degrees, but this can be reduced in the advanced support options during job preparation if you desire. This isn't necessary though, and it's typically best to keep that number somewhere around or above 45 degrees. So in the top image shown here, there are two overhangs. One is at 45 degrees from horizontal, the other is at 50 degrees from horizontal. The 40-degree overhang is too shallow for the default self-supporting angle settings and will require removal of support. The 50-degree overhang, however, does not require any support removal. In more complex and less accessible geometries, this distinction can make a significant difference in the amount of support that needs to be removed. So it's important to consider whether a shallow build angle is necessary. The three images shown below illustrate how self-supporting angles can eliminate the need for support from delicate features on the left and deep cavities on the right, making post-processing of these parts much simpler. So as you can see on the left, the delicate features that had horizontal surfaces on the bottom previously now have self-supporting build angles, which will mean that no support needs to be built underneath them. On the right, you have a deep cavity, which previously had a horizontal surface at the top, but now it similarly has self-supporting build angles that will prevent any support from being needed inside. A related strategy to self-supporting angles is the teardrop cavity. As shown in the image on the right, a circular hole of sufficient size will require support to hold it up, while a similar hole with a self-supporting top surface does not. Consider whether this strategy would be appropriate for your part. In some cases, removing that material at the top will not be appropriate. Using this strategy can eliminate the need for support for all sorts of internal cavities, which can reduce the duration of post-processing, but also enable you to create complex internal or obstructed channels that would not otherwise be possible. So in the image on the bottom here, you can see that two channels, one circular, one teardrop shaped, were cut through this part in a curved, along a curved path. And in the case of the circular hole, this path would be very difficult to get all of the support out because it's so deep and narrow, and there would need to be a special set of tools in order to reach that far and extract the support. But in the teardrop-shaped cavity, no support would be generated, and you could have even more complex pathways than this. So this pathway has a slight curve, but you could have a pathway that travels all in different directions inside the part. And using this strategy, you could do it without requiring any support inside. So another related strategy is to put self-supporting reliefs at the edges of bottom surfaces. This can reduce the amount of surface area on the model and support interface, making it easier to detach the supports. It also leaves a space at the edges of the support structures that makes it easier to hook your tools in between. This approach allows you to speed up support removal while keeping the same shallow or horizontal surfaces on the overhangs of your parts. And it can help with several kinds of support removal challenges, including deep cavities, broad bottom surfaces, and delicate features. So the parts shown here, the part on top, for example, has two deep cavities. One of them has reliefs at the edges with self-supporting build angles, and this means that a smaller portion of the top surface needs to be supported. This fact allows you to reduce the amount of surface area on the interface between model material and support material, and this smaller surface will be will make it easier to extract the support. It also leaves spaces between the model and support at the edges, which makes it easier to get tools in between and extract them. So on the lower picture, you have a very similar situation, but instead of a deep cavity, it's a broad bottom surface. And in the same way, you have these reliefs at the edge, which slightly reduce the amount of surface area on the interface, but they also leave a space at the side, which makes it much easier to hook your tools underneath and in between the model and support material. So that should also make it easier to extract the pieces. Now, a different strategy is to orient parts differently to improve support removal speed. The orientation that you choose during pre-processing can affect many different variables, and choosing the right orientation involves balancing those effects with your requirements. Orientation affects the amount of support that gets used to build a part, but it also affects the speed of support removal which in extreme cases can add quite a bit of time to post-processing. The parts shown here, if printed laid down, would fill all of its gaps with support that could be difficult to extract. Printing this part upright instead would only fill a small portion of the gaps, and the support structures would only attach to the model on their narrow top surfaces rather than their full lengths, making it much easier to extract them. This reorientation approach can apply to a wide variety of geometries and can be applied to great effect in tandem with the other design strategies I've discussed here. A final strategy is to consider the features that are giving you the most trouble during support removal and consider whether the function they serve is necessary. In some cases, a feature may have been created for the sole purpose of reducing material usage, and if such a feature results in additional support structures, then it is best to remove it. Other features may be causing trouble while serving no purpose at all, and such features should of course be removed. There are many other things to consider along these lines, so essentially you'll just need to consider what sort of complexities are involved in your parts and consider whether any of those complexities can be reduced to make support removal easier if you're having trouble with that. All right, that's all I have for you today. Thank you for attending this webinar. As always, you can reach us at applications@rise3d.com for any questions or concerns you may come up with. Thank you again for attending our webinar, and I'll see you on future webinars.